Ladies and gentlemen, thank you for joining us today, both in person at JSCE and Zoom online. こんにちは and 안녕하세요. My name is Panjo Chun from the University of Tokyo, and I will be serving as the moderator for today's symposium, Digital Construction in Japan and Korea, organized by ACECC TC30. We have a total of 6 presentations today, and 3 from Korea and 3 from Japan. My role as the moderator will be simple, but I hope we can have good discussions and good presentations. I have several points I would like to ask you, especially for the Zoom audience. Please turn off mic and camera in Zoom. This is the first point. And the second point, if you have questions and comments, please use chat function of Zoom. And at that time, please include your name and affiliation in the comment. And I am sorry to tell you that due to the time constraint, we may not be able to answer all of your questions, but we try to answer your questions. And this symposium, TC30 is now we are in Japan, and there are lots of Korean. So this symposium mainly conducted in English, but sometimes we may have Japanese and Korean. So please forgive us about that. And yes, this is what I want to say as the moderator. And not only as the moderator, I also have the honor of delivering the opening remarks on behalf of the JSCE. And it is my great honor to welcome you on behalf of JSCE to this symposium. I am proud that we are able to host such an event today. I hope this symposium will serve as a starting point for good exchanges of ideas or techniques and so on between Japan and Korea, as well as within TC30 or other Asian countries or all over the world. Now, I would like to read congratulatory messages from JSCE and KSCE. And this is from JSCE Executive Director, Mr. Miwa. Dear Dr. Cho and Professor Chun, TC30 members, distinguished guests, colleagues, and friends. It's my great honor and privilege to hold TC30 Seminar, Digital Construction in Japan and Korea at the JSCE HQ today. We are standing at the forefront of a transformative era in the construction industry, driven by unprecedented advancements in digital technology, and this seminar will provide us with the present and the future construction industry landscapes. On behalf of JSCE, I extend my warm greetings and best wishes to you for the success of this seminar. I also like to thank to KSCE, my JSCE colleagues, and the Asian Civil Engineering Council, ACECC, for support and cooperation to establish the TC30, which focuses on digital technologies in smart construction. Experts from KSCE and JSCE have collaborated closely and taken leadership roles in developing TC30's initiatives since the beginning of the TC. I trust that they will leverage the efforts, knowledge, and experience to deliver significant outcome, and then will contribute to the advancement of smart construction. Again, let me express my sincere appreciation and gratitude to the co-chairs, Dr. Soon Min Cho and Professor Panjo Chun, all the committee members, and last but not least, KSCE President Chun and KSCE colleagues for their continued support and cooperation. Sincerely yours, from Mr. Miwa. And one more message from the President of KSCE, Chun. A greeting from the President of the Korean Society of Civil Engineers. KSCE and JSCE academic organizations representing the civil engineers field in Korea and Japan have maintained a mutually beneficial relationship based on trust since signing the agreement of cooperation in 1989. With the digital transformation of industries, now an unavoidable and critical global issue, the construction industries in leading countries face a major opportunity with the advent of smart construction. This technological shift in the construction industry is already a global phenomenon, particularly in advanced countries, where digital transformation has become a key issue. However, unlike other industries such as manufacturing, the digital transformation in the construction field is very challenging, making it essential to share and discuss knowledge and experiences. It is significant that the ACECC, of which both organizations are members, established the 30th Technical Committee dealing with digital technologies for smart construction 2 years ago. It is particularly valuable that experts from KSCE and JSCE are leading the operation of the TC30. Korea and Japan share many similarities in promoting smart construction, particularly in the leadership roles played by the government and the public sector in driving industry changes. I consider it highly meaningful to hold an important seminar in Tokyo on the topic of smart construction to share the experiences and knowledge of both countries with ACECC members. I appreciate Dr. Sang-Min Cho, chair of the committee, and Professor Panjo Chun, co-chair, and all committee members. I also sincerely thank JSCE and President Shigeyoshi Tanaka for sponsoring this event. KSCE will continue to collaborate with JSCE and ACECC to revitalize the digital transformation of civil engineering technology, academics, and construction industry. Best regards. Thank you very much for the message from JSCE and KSCE. Anyway, thank you very much for the messages. And okay, then let's start the presentation sessions. And let us move on the first presentation. Maybe Dr. Cho, can you make?
Good morning, everybody. I am Sang-Min Cho from Korea Expressway Corporation, and I am a chair of TC30 of ACECC. Today, I will speak about Korea's policy and the national research program on smart construction. As you know, digitalization already was the new normal to change our construction industry recently. And my organization, KEC, is the competent authority for National Expressway System of the Republic of Korea under the Ministry of Land, Infrastructure, and Transport. Let me introduce the ACECC and the TC30. ACECC is the Asian Civil Engineering Coordinating Council, which was established in 1999 with the 5 societies at the Asian and Pacific region. And the main purpose of the ACECC was to promote and advance the civil engineering technology and the science and the related professions for sustainable development in this region. And ACECC established the technical committee number 30 2 years ago to share information on digital technologies in the construction industry, such as BIM-based digital design, virtual construction, robotics, artificial intelligence, and other automated construction equipment. And I am the chair, and Professor Chun is the co-chair of this technical committee. Professor Chun already introduced the greetings from the president of KEC. Thank you. My organization at the Center for Smart Construction Technology is a managing body of the national R&D program to develop smart construction technology in Korea. And this center is responsible for implementing the research program demonstrating developed technologies and promoting smart construction technologies in the construction industry. This center is belonging to the KEC, National Expressway Authority of Korea. And there are 4 large groups from group 1 to group 4. And today's presenter, Professor Seo, leads the research group 1. And the second and the third presenter of the Korean side, Professor Shim, is leading research group 2 for the automation of structural construction. Smart construction can be defined as a system of applying advanced digital technologies, such as so many digital technology, innovative technologies to traditional construction system, aiming to enhance productivity through shortened construction periods and reduce the labor power, while improving on-site safety and quality, and promoting digitalization, automation, and prefabrication at all stages of construction, from the design to the construction, as well as to the operation and the maintenance period. And this was the definition from the Korean Ministry of Land, Infrastructure, and Transport. I'll show some brief timeline of smart construction policy in Korea. This was originally based on the previous research program for virtual construction system in 2006. Professor Seo led this research program. And in 2008, Korean government made a technical roadmap to apply the BIM in Korean construction industry. And at the time, Korea firstly applied BIM to architectures. And in 2009, the BIM was introduced in civil engineering structure. And in 2016, the National Expressway Agency, KEC, made a detailed guidelines to apply BIM for the design of the National Expressway of Korea. And in 2017, Korean government reflected the vision of smart construction in to the National Comprehensive Master Plan for Construction Technology Promotion. And the next year, in 2018, the roadmap for describe these digital technologies for smart construction was established by the Korean government. And following this technical roadmap from 2020, Korean government commenced the ambitious national research program to develop digital technologies for smart construction. And we KEC has managed this program from 2020 to present now. And we KEC mandated the BIM only design for National Expressway from 2021. This is the graphical representation of historical recent trends I just explained before. From this master plan was established in 2017 and the roadmap in 2018, and a national R&D program launched from 2020. And now government revised the strategic plan in 2022, and the new vision of smart construction was reflected again into the 7th master plan for construction technology development last year. There are 3 strategic items to promote smart construction in Korean construction industry. The first one is to digitalize the industry through full introduction of BIM, CIM in Japan saying. The second is to advance the production system for the structure. So that is based on off-site construction or modular or prefabricated system for the bridge or tunnel, as well as for the architecture system. And finally, to foster the smart construction industry, this is bringing up the ecosystem for digitalized construction industry. The National Research Program for Smart Construction in Korea consists of 12 projects for 4 core sectors. The first sector is to automate the earthworks and including a digital mapping for the field geospatial information. The second is for automated structural construction and application of prefab for bridge and tunnels. The third one is to enhance the construction safety through the fully application of digitalized techniques. And finally, to make technology and to establish the digital platform to handle the data produced in field site. So we are now developing 140 detailed digital technologies for this. So this category of our research program to develop digital technologies for the digitalization or digital transformation of our construction industry. So our target is to make paperless construction and change the construction industry to manufacturing industry. And thanks to this, we are aiming to make 7-dimension construction from the digital transformation of our construction industry. I briefly introduced 4 major sectors for this program. The first one is the earthworks automation and the site data collection. We are developing technologies by integrating the site information acquired through autonomous measurement using drones, unmanned ground vehicles, including a robot, and various sensors to create a high-precision digital map and combine it with the equipment automation for road, especially for road construction. I will show 4 videos. Please understand that I make a video very fast to save the time. This is the introduction of the first major sector, mainly for automated and unmanned earthworks construction. So we introduced this technology to actual field site for National Expressway last year. And KEC is now applying this technology to actual National Expressway project. And the Professor So will introduce this in detail. We make automated technologies for motor grader and dozer and compaction roller. You can see the empty cabin according to the target model. Yeah, this is the first sector. And the second core sector is a prefab and the design for manufacture and assembly process and automated structure construction. This will be introduced by Professor Shim next time. We are developing the technology that employs BIM, artificial intelligence, and 3D scanning, prefabrication, and robotics to improve the design, fabrication, construction process, and support collaboration between each process to build bridges and tunnels. So this was mainly based on the digital model, like as building information model or CIM. I show a video again. And this is for bridge site. And the deck or slab for bridge was manufactured automatically in the factory and moved to the field site. And this is show 3D printing and the scanning in the field site for, using a digital model. And during a transportation to the field site, it can be monitored for the check of integrity of structure members. And as you see, the robots will erect the bridge girder automatically in the field site. KEC will introduce this technology in actual construction site for the National Expressway from next year, including artificial intelligence operated tunnel boring machine project. Yeah, the third core sector is the smart construction safety. So we are developing technologies using a digital twin-based smart safety integrated control system using cloud, big data, AI, IoT sensor network, and edge computing for implementation of a safety construction now. And yeah, we already checked the dual trend of AI that is a kind of on-device system. So we are now developing those kind of technology also. This is a video to describe this the third core sector for smart safety. Yeah, proximity warning of construction equipment and so many IoT and on device for the safety of working people in the field site. And training prior to job in field site using a BIM-based content to educate the people to recognize the safety. We show digital twin-based field construction management system. The final core sector is to share digital data for stakeholders in the field site and to establish digital platform to handle this data and to adopt digital twin-based environment system for construction management in the field site. The final video to show this. This is a control center for field and construction project. We can manage whole thing digitally in the center for actual construction site. This technology has been used for actual National Expressway construction project now. And the whole data from the equipment, sensors, and BIM-based data model can be integrated at this digital platform. And the AR or VR technology can be combined also. I introduced a major core factors for our national research program for smart construction in Korea. And you may already recognize, we think, the digital technologies for construction industry will be a new horizon of construction and infrastructure in near future. Thank you very much.
Thank you very much, Dr. Cho. And I will do the moderator from this desk. And if you have questions, we can ask, we can hear about. No, then we'll have later question and answer session later. So let's move to the next presentation, Dr. Moteki.
I will talk about ICT and unmanned construction in Japan. Today, I will talk about ICT construction and unmanned construction. In particular, I will introduce some of my research results on unmanned construction. My name is Masaharu Moteki. I belong to Public Work Research Institute Advanced Technology team. My major is cognitive psychology and ecological psychology, and human interface and machine control. Now let's talk about ICT construction. Japan has set the goal of 20% construction productivity by 2025. To achieve this goal, 3D surveying by drones and construction with ICT construction machinery and labor-saving inspection is being introduced to a construction site. ICT construction equipment is enabling IoT through 3D design data. I-construction is taking the automation of construction sites to the next step. This is just recently the Ministry of Land, Infrastructure, Transport and Tourism recent cited the I-construction version 2 as the next step. The goal is to save 30% of manpower, reduce fatal accident and remote construction. Regarding manpower saving, we aim increase productivity by 1.5 times. Top runner measures for automation in construction site. As for automation of construction site, we will advance, improving the environment for automated construction and expanding the use of remote construction. Next, BIM, digitalization and data linkage. Next, construction management by remote. Through these, we will realize automation of construction site. However, as a reality, what is the utilization of construction machinery, automation, and remote operator technology? Automation and remote control are difficult to achieve. Currently, unmanned construction is being used for disaster recovery or impact of dam construction. Therefore, there are challenges in general construction work. I'm not familiar with dam construction automation. Where Kajima Corporation and Taisei Corporation and overseas knows about automation of dam construction. Next, let's take about look it. However, I would like to introduce unmanned construction. In Japan, about 1,000 landslides occur annually. It is increasing due to climate change. Japan has experienced major disasters shown. Unmanned and Great East Japan earthquake. For example, massive volcano pyroclastic fall in Unzen and Great East Japan earthquake. Volcano and earthquake. As I shown earlier, unmanned construction is utilized at the disaster site. Utilization of disaster and unmanned construction. Unmanned construction has been actively utilized in Unzen since the 90s. Unmanned construction is then 10 to 15 cases per year being utilized. What is unmanned construction? Unmanned construction consists of a remote control room and construction equipment equipped with camera and radio equipment. Initially, there were delays due to communication. However, that problem has been solved. The utilization of unmanned construction technology in disaster recovery activity. The unmanned construction is a remote control by direct visual observation as an initial response after disaster. This is done to secure the transportation route for recovery. Next, determines the risk. If the risk to workers high, unmanned construction with operation room. Unmanned construction with operation room when the risk to worker is small. Mechanical construction, including human labor. In the future, automatic automation construction. 韓国語で示しております。Next, utilization of unmanned construction. Here is the status of the utilization of unmanned construction. In the initial response after disaster, remote operation by direct visual inspection. Long-term safe assured unmanned construction. Remote operation from the remote operation room. Next, I will describe the challenges of unmanned construction being utilized. The major challenges are the lack of operators reduce efficiency. In particular, work efficiency is twice as high as in normal construction. Therefore, it is necessary to understand the actual situation in order to solve such issues. I would like to present some of our research at the PWRI. A model task was set as a standard operation with a hydraulic excavator, mainly assuming excavator and loading work at the real site, and was performed 10 times per operator. I experimented with scooping and with hydraulic excavator. Situation of the experiment of unmanned construction within Public Work Research Institute. I have conducted experiment to determine the actual work efficiency of unmanned construction best. The situation is operation using the conventional remote operation device. And next, the station is operation using the cabin type remote operation device. The station is a visual remote operation from a high place. Next, the station is remote operation from the ground. This operation. The station is operation with remote operation device, remote control unit about the machine. This operator. Next to the experiment confirmed the visual. Analysis using the IMAC record. This IMAC record. The monitors were placed based on the visual experience. The station is operation using the conventional remote operation device. Visual information increased と増やしてます、これは。Next, the station is operation using the cabin operation device. Visual information increased. Monitor increased. Yes. There are the experimental result for various operations. All the at the experimental level. Cycle time cabin reduced by enhancing visual information. Visual information and operation interface related to the improvement of work efficiency. Device found to be a 30% improvement over conventional system. The station is operation using the cabin type operation device. こちらにです。Next, in addition, the PWRI is also conducting research on other systems using head-mount display. Based on research results, deployment of remote control technology for use at the construction site is being promoted. Finally, our future research. I would like to proceed with the collection of basic data. Also, I would like to study human cognitive information processing and propose a system. Research result, I believe that the result of our research will lead to the promotion of ICT construction. Thank you very much for your kind attention.
Thank you very much, Dr. Moteki. And though we have one question from the Zoom, but later we will have the question and answer sessions. So we will answer at that time. And he kindly introduced the previous research in Japan about the unmanned construction in the public sector. And thank you very much, Dr. Moteki. And next presenter may be Dr. So. Can I ask you to make the presentation?
Very nice to meet you, all of you. I am Jongwon So of Hanyang University, and I am very happy to participate in this special ACECC TC30 Seminar, and I thank JSCE and KSCE arranging this seminar. This is my bio. I am a civil engineer, but in 1998, I wrote a thesis, PhD thesis about machine control, machine guidance, about a robotic power plant maintenance equipment. This is pretty old, right? 26 years ago. But I still work on this topic today. And before I joined the universities, I worked as a 3D modeler. Back then, we didn't have the word BIM. So I was a 3D modeler and designer for especially road and land development projects. And I was lucky enough to direct 3 big size research in Korea. The first one was about the excavator automation. That was from 2008 and 2012. So it's been a while. And the second one and the third one is more about the fleet management or earthwork automation platform research. And I served as a board member for International Association for Automation and Robotics in Construction. And I served as a academic vice president for KSCE last year. And now I am serving as a president for Korean Society of Automation and Robotics in Construction. My topic is quite similar to the previous presentation by Dr. Masaharu. Yeah, it's about earthwork automation. There are some unmanned part or also a manned part. A little bit different approach. We are not looking at just unmanned construction. We are looking at the mixed level autonomy, and we are looking at advancing the automation level for not the machinery itself, for the site, for the whole site. So more of the systematic approach. This is already explained by Dr. Cho, and as Smart Construction Plan of Korea, the first axis is the digitalization. It's a beam throughout the entire construction process. And what I'm talking about is the about this second axis, advanced construction production systems through automation of a construction machinery and development of robots and off-site construction, also safety systems, safety equipment. So talking about automation, why do we need automation? We always say above 3 items: productivity dilemma, safety issues, labor shortage, and we have another issue about environmental and energy issues to achieve automation. What is the most important reason now for automation? As I have the bold character there, it's a labor shortage. We're not facing the labor shortage problem. We are experiencing serious labor shortage problem now in Korea. I think it's the same is true for Japan. The really difficult to find the dozer operator who are younger than 60 years old. Really. I am close to 60 years old, and all my colleague those operators they are more than 60 years old. And even the more serious problem is no young generation people are coming into this equipment operator business. So it's a problem. So we need to solve this problem by automation. So let's get into the earthwork automation. We have 3 sections to achieve earthwork automation R&D. And first one is a fleet management platform or automation platform for Earthwork. You know, left side is a platform side. We have a cloud-based E-beam. That's a 3D design module, actually. And second one is a fleet management. It's a beam GIS-based path planning, path monitoring, productivity control, safety control, kind of fleet management module. And the right side is the smart network systems and positioning systems. The bottom one is the remote control technology. Second section is about using UAV and UGV for obtaining autonomous digital map. And also geotechnical properties and other environmental data are automatically collected and analyzed. Third one is the equipment itself, automation of equipment itself. We are retrofitting existing commercial equipment to automated unmanned equipment. It's about using a robotic control block to control hydraulic valves of the commercial construction equipment and using necessary sensors. And the second one is pretty important. So automated quality control. We have automated equipment and they are doing the work automatically. But let's think about if the quality control is done manually, then the quality control process becomes the critical path. So we looking at the quality control process as a very important item to automate. So compaction quality management, also roadbed profile quality management are done automatically. So these are 3 sections. And we are at the last stage of development. Last year, we had a big demonstration at the major highway construction site. Dr. Joe showed the video. This is a president of the Korea Highway Express, Korea Highway Corporation, and you already saw it. And you see this UGV. Drones cannot cover all the area, so we are utilizing UGV to get the digital map. They are quite autonomous by giving the waypoint for UAV and the UGV. And it's a platform side. I'll explain this in detail later. Looks like a hardware is like equipment are automated, but all the works are done by the software technology, digital technology within the platform. So this now HD InfraCore HD people is here now, and they are working on retrofitting their new dozer, and I think it's on the market right now, and it's a CAT radar, and we have retrofitted OMEC roller. That's important. We are not creating new automated equipment. We're retrofitting, so we can export this technology to any equipment manufacturer. So let me get into the automation platform. This is the picture of this mobile fleet control center with the cloud-based program is running within this mobile control center. You can control the all the automated equipment from the more remote side, but we have some edge computing issues to get the IoT sensors from the equipment. So to do so, we have a direct telecommunication by placing this mobile control center closely to the construction site. And as you can see here, this is called access package, and it can cover like a 200-meter coverage. It's like a router for large area, wide area, and you can put other access packages in relay, and you can cover maybe 1 kilometer, 2 kilometer area easily. Inside of the mobile control center with this remote control station, the unmanned equipment can be controlled autonomously, following the passes, or you can remotely control by using this remote control station. And I saw Japan's effort on this remote control, and we are using visual feedback as well as the model feedback, meaning we are using augmented reality within one screen. So it's like combining machine guidance input as well as a visual feedback together to make the remote control easier and efficient. And this is the structure of the cloud platform. Two modules. E means Earthwork, E-beam, E-fleet manager. E-beam is creating or processing drone data to come up with a thin digital model, and it has the 3D design capability for road and land development, creating target models and processing alignment data. And finally, you can create the passes for the automated equipment. And the fleet manager side, it can monitor the productivity. I'll talk about the importance of the productivity monitoring a little later. And pass management. You need to take a look at whether the machines are moving correctly or not. And it can even do the invoicing, especially for dump trucks. You need to figure out the loading was done correctly at the right site, and unloading was done, of course, maybe at the construction site itself. And you need to find out the travel distances. And finally, you pay the dump operator, recognizing you've done the work correctly. Okay, next one is the IoT-based safety systems. Oh, I need to talk about. As I said before, we're not just looking at the unmanned machine. The MC equipped machines, unmanned machines can be managed by this cloud platform. This cloud platform is not just for the unmanned. It can even manage just conventional machines with the GPS attachment. So when you have a manned operator and manned equipment, you need to put EMAP mobile unit. It can be installed on the smartphone of the equipment operator, so that it can follow the path. He or she can follow the path. Difference, machine guidance, they don't give you the passes. They give you the target. So we see that this is the difference. And of course, for unmanned machine, the platform creates the passes and send it to document. And this is it will be exhibited next year at the CSPI, but it's not fully retrofitted. It's called the master slave control. Before, it was controlled by a joystick outside. now that control command is moved to the cloud platform so that you can work on the passes created by the platform, and this is like replacing operator's hand and foot. The point is, it's retrofitting this way is much easier to the retrofitting all the internal equipment systems or adding robotic control blocks into the circuit of the existing equipment. So again, MGMC unmanned or conventional machines are managed by the cloud platform. Let me start with the E-beam. All the models are the models created for the demonstration construction work that I showed you on the video. Isn't it similar to that construction site from the that video? And this E-beam can process the drone data, meaning the point cloud, the many pixels, and you need to come up with these the digital map, triangular irregulation network map. Next one is a target model generation. It's like a civil 3D or Trimble's business center, TBC. You put alignment data and you make a 3D design model for the target of the equipment, and it's a 3D. It's kind of hard to tell the difference between original ground and the target, but it is the cross-sectional view of the target model. And route planning. We come up with 3D cells to create equipment passes. You see, we had three different equipment at the from the video, and the longer one is the compactor. We have the grader and dozer, and the parameters such as the blader's width that should be controlled. They should be considered to make the size of the cell correctly, and basically those cells are original ground, and the movement of the original ground is the movement of the equipment. Okay. Now, fleet manager side. This is a very critical and intuitive interface. You see the design data at the boundary of the site, and those boxes are like virtual fences, so that the equipment cannot. They work within the work area, that virtual fences. If it goes off the boundary area, there'll be the signal or even the emergency stop. And the previous interface looks like a 2D, but it is a 2D view of these 3Ds. All the calculations are done in 3D, but actually for monitoring and the controlling actual equipment, this is more efficient. And this was exactly my topic for my thesis. Which view is really helping the operator or controller? Confusing, actually. And next one is important one, equipment trajectory. You know, the every second we update the equipment position, and it'll be saved as a data log. So the red one is a wrong position, and the blue one is a right position. Why so many red ones? This was the starting point of the demonstration, and they moved to the demonstration point. So starting point. So for the demonstration, all the pass was correctly performed by the equipment, and this is used as a big data for later the pass planning. So it's we are collecting all the data every time we are on the construction site. And this productivity report and productivity monitoring, by only using GPS data, we were able to find out whether equipment is going forward, pushing forward, or steering, or pushing backward. That is the one cycle of the this kind of dozer and grader type equipment, and that cycle time is the key for monitoring the productivity of each equipment. Only one equipment, the productivity monitoring, it's important, but the more important thing is getting the productivity data of different all the equipment fleets, and that data, productivity data, is really important big data for coming up with the best equipment combinations for later project. So, for example, let's use one or two unmanned dozers and one unmanned roller, but MG-based. Let's put MG-based grader. That's the forming the combination of the fleet. And I talked about a little bit already about this virtual fence thing is quite useful, you know. This is about productivity. This is also about the quality, and we have many landfill site in Korea. You know, getting soil from remote site and fill it to come up with a new construction complex, and kind of and you need to have a good soil. And we had some problems getting good soils, and to prevent getting bad soils, the dump should go to the correct loading site, and these are all checked by this platform. Actually, this cloud platform for Earthwork automation has been commercialized, and I transferred this technology to this company, and it's been released, commercial version, and I think it will be exhibited next year's CSPI. I visited the CSPI this year. I see like a quite similar approach from Hitachi's platform, and even the mobile control center is pretty similar to ours. I don't think I saw it last year, but I saw it this year. Okay, the final topic: how do we approach to promote construction automation? Do we have to do construction automation just because it looks cool? Maybe not. Serving as the president of the Korean Society of Automation and Robotics in Construction, I get many questions about this, and Mr. Masaharu also talked about the slow speed of the unmanned operation and all that. Let me ask you questions, or we can discuss about these issues later at the discussion session. The first one: as you saw, the unmanned machines are slow. Should we use? It's compared to manned operation. If it's skilled, said Japan, about 50%. Our goal for the productivity of the unmanned construction is like for each individual equipment, we look at like a 70%, 80% of the manned operation by the skilled operator. Then, why do we have to use this with the low productivity of the autonomous or unmanned machine? Question. Need answers. And as I already said, the effort for the fully retrofitting existing equipment is expensive. And current OEM, original equipment manufacturers like a CAT or even here Hitachi, and they don't produce a unmanned machine. They do R&Ds, but not yet. So every time you use unmanned machine, you have to pay this kind of money to come up with a full retrofitted automated machine. I need to give them the answers. The third one, we spent like more than 20 years to make autonomous vehicles. But do you see fully autonomous vehicles on the road? Not yet, because of the safety issues. Are we better when we make the construction equipment autonomous? Is it better? Safety-wise, let's think about and discuss. And this is the last slide, and I see the automation and autonomy as the systems approach. As I said before, we need to use mixed level automated machine and increase the autonomy of the job site. Of course, the autonomous machine is part of it. And this word, I took it from the last year's Trimble has a conference, and that was a Caterpillar. The same opinion as mine, and automation in construction is a workflow automation, dispatch to a mixed of manned and autonomous machine. And, I showed the fleet management or automation platform. You need this kind of platform to come up with a control system for mixed level equipment, maybe, or even the human. Thank you for listening.
Thank you very much, Professor So, and thank you very much for raising the discussion topics in the final slide. And next presenter is Professor Nagatani from the University of Tokyo.
Thank you for your introduction. This is Keiji Nagatani from the University of Tokyo. And yeah, it's a nice talk from the Professor So. And I have some answer from your question, or I may have interesting topics inside on my slide, I hope. But anyway, I'd like to introduce our project. It's just started from the 2023 in Japan. And it includes, today I'd like to introduce our motivation, why we start this project. So, but before that, I would like to speak my introduction. I was born in 1968, so I'm almost 60 years old. No, not yet. But anyway, we have the same problem as Korean people. But the important part of this slide is I faced several disasters. You see, in 2001, accidentally, I visited to the United States and I faced the 911. And 2011, I was living in Sendai. Sendai region is the north of Japan, and we had a very serious earthquake. Then this is my kind of history, and the important part is I faced several disasters. Then one of the disasters in this is a Fukushima Daiichi nuclear power plant. When we faced this disaster, I had one project of the disaster response robot, and our robot was rebuilt to put the robot into such kind of environment. When we faced or we are working on this project, I found that we need to have more reliable robots or reliable machines. So this is my background. So I am a robotics guy, not comes from the civil engineering department. So at the beginning, we are studying. I'm studying on the mobile robot inside, very small and easy to operate. But my project was an intelligent robot, and after the March 11th, the big earthquake, I saw that I needed to move to the very real world. So then started working on the drones and the construction machines and disaster response. Then now I'm working with Professor Ozawa in the University of Tokyo and making researching on the automated construction and so on, and disaster response. So today's topic, I have several projects, and one of it is about disaster response. But today I like to focus on the this one, SIP project. This is the SIP is a cross-ministerial strategic innovation program, promotion program. And I'm in charge of the issue 9, Smart Infrastructure Management System. And I'm a program project leader of the sub-issue A, Innovation in Construction Production Process. So we named this project SIP-ICAS Project. So Innovative Construction and Surveillance Technology with Unmanned Machinery Project. So it includes 4 divisions. I don't have much time today, so I like to focus on the A1 and A3. The A1 is autonomous earthwork for total optimization of construction process. It's automated construction. And the third one is the second one is autonomous constructor for tunnel blasting. So I led I heard your presentation, and you are some guy comes from the construction of the road or something. Then you might be interested in this project also. So I like to start the background of this project. I don't have to speak about this. So you already also the same situation. The important part is 55 and over is a percentage is increasing. And the background of the another background is a value added labor productivity. So you see that the manufacturing in Japan, the manufacturing productivity is going up, but the construction is not so going up, not so much. Then it means that this division, the construction industry, has the potential to significantly improve the productivity. So I hope. So I said that I'm a robotics researcher. Then I'm trying to do something based on such kind of robotic technology. So this is the final goal of automated earthworks. The human being be sitting down inside everything is done in the outside. But of course, it's a bit far from current situation. So now we are working on the, this is another project. So it's automated earthworks with 6 construction machines. Each has a retrofitted device inside of the truck vehicle. And also this guy works autonomously with some laser range finder to get whether this machine get the soil. And this other backhoe excavator is working teleoperatively. So this is one result of not the SIP project, but the moonshot project I'm still working on. So I showed this video clip to the one general conductors. Okay, this is good, but he said it can't do a job. This is a motivation, one of the motivation from this SIP project. The current automated construction technology can make motion of construction machines. I said motion, but it cannot do a job. So we started thinking about that. And one important part is dandori. Dandori is a Japanese word. So Korean guy said to me, dandori is almost the same pronunciation. No, you already know about the dandori. So it's interesting. But I recall that the scheduling, arrangement, and preparation. So the construction guy said that dandori occupies almost 80% of the entire work. However, in typical autonomous construction demonstration, or you see in the CSPI, then the construction machinery guy showed a very fantastic presentation, but we see the only 20%. And in typical autonomous construction demo, dandori is conducted by human in advance. So the guy said that it's another 80% is required. Then in Japan, the autonomous construction with dandori is conducted by, I can say the Kajima only. The Kajima's guy already demonstrated the dam construction. However, the target is to construct CSG. You might know about that, cemented sand and gravel dam. The soil is very good. And also the area of the construction is limited. And the technology is not applied to general earthwork practice directly. So we think that the systematization of construction procedures for general earthworks is insufficient. So what is general earthworks? Excavation, loading, transport, release, spreading, and compaction is one set. And it's not cover the whole earthworks. However, it can cover many big percentage of the construction. Then we focus on this general earthworks, and we made a team with several universities and the PWRI, and also general contractors. And important part is we made a team with both robotics guy and also civil engineering guys. Civil engineering guy includes general contractors. So then we are now working on it. So I don't have much progress because it is just started. However, I hope I could send a message or the motivation of our project. So another important topic in this project is to change the structure of the research. So in the current situation, we have several good research results or in Japan. So, but typically they have groups, one construction company and a system company and also machinery company. That includes maybe Komatsu or Hitachi or some others. So, however, they have a group and it's very difficult to communicate between the groups. Then we are now thinking about the common interface. Once we can define the common interface between the construction company and the system company, or the system company and the machinery company, then we can change the team of the, or we can use other developed research results. So in this research, in this project, we are now working on a collaborative or cooperative area. So one example is Opera, which is proposed by the PWRI. It includes several, one important common layer that is a common communication message from the construction machinery. It means that once we define the signal, the control signal to the construction machine, then we can use the different companies' construction machinery. So we are now, PWRI is now working on the set up such kind of the interface. And another interesting part is we are using middleware called ROS, Robot Operating System. It is very common in the robotics society, and we can share some algorithm of the optimization or planning or using the sensors based on the ROS system. Then this is another aspect of our project. So next, I would like to move on to the automated construction for tunnel blasting. So tunnel excavation technology is, you see, the very dangerous work. And in the first presenter's slide, there was a sealed machine to dig the tunnel. But in this project, we are focusing on the very standard tunnel blasting. I forgot the name of the exact name. Yeah. So so this is the process of making a hole and putting exclusive loading, wiring, ignition by human, and mark removal steel supported, and shotcrete and rock bolt drilling. So this cycle make a tunnel. And the important part is exclusive loading, wiring, ignition currently by human. So other part, the Japanese general contractor is now developing a good robot or teleoperated machine. However, the final part, wiring, is made by human. This is a very, very big gap between the automated tunnel construction and the current. The technology for remote loading of explosive is advanced, but the wiring of detonator is still done manually. It's a very dangerous. You see, it happens. Actually, several years ago, we had such kind of accident in the actual tunnel. So then the solution should be the wireless electric detonator system. Then we don't have to wire to blast such blasting materials. So then we can have ensuring safety. It should be important. So in this project, there are several companies and universities is now developing the wireless electric detonators, and the wireless technology is the key. So it means not only the technology, but also the radio law part is also important. So one company, NOS Corporation, is now developing the wireless electric detonator system and the verification of the safety. And the University of Electrical Communication is development of the communication method for wireless electric detonator system. And 3 general conductors are working with us, Kumagai Gumi, Taisei Corporation, and Maeda Corporation. These guys are included in this project. And finally, coordinator is JCMA, the overall coordination, the Japan Construction Machinery and the Construction Association. So then this part we are just making. Now we are working on developing the wireless detonators. So this is the last slide, and we have another 2 projects, but I would like to skip today. Then that's all of my presentation. Okay, thank you very much.
Is Professor Shim from Chun University.
Good morning. My name is Changsu Shim from Jongwon University. I'm going to explain our research efforts to digitalize the process from design, fabrication, and finally the construction, especially for assembly of prefabricated bridge members. So during the last 4 years of our research program, we defined new concept of bridge structures. It's prefab. I will explain in detail for resilience. Resilience is a new value for the infrastructures. And we also need to adopt a new concept of DfMA. DfMA is originally the concept from manufacturing industry. Designer need to consider the efficiency of fabrication and also the assembly process, right? This is common sense for the manufacturing industry, but in construction industry, we lack of this kind of concept. And also I will explain some examples of our research programs from the manufacturing and also the concrete printing and also the geometry inspection and the assembly using robots. This is a new concept naming for the structure. Prefab start from the prefabricated. Designer should consider how can be fabricated in a factory, and also how to inspect in digitalized way, and also we need to have the pre-assembly before transport the members to the site, right? So we have to find out any adjustment plan before the assembly. And resilience is very important part. As you know, we have much the infrastructures deteriorated for a long time, and we also have the man-made or the natural hazard. So we have to open the service as soon as possible. So the prefab structure is proper to solve the challenging issues in structure industry. And also the prefabrication has advantage of minimum waste during the fabrication and also the construction. Of course, we can reduce the CO2 emission from the adoption of the prefab structures. Future-proof, we monitor or collect the data from design to construction. And also in the future, we will collect the data from the maintenance period. Using these data, we will develop the data twin service. So we can evaluate and predict the structural performance. So it will be much more reliable. So we can predict the service life of each structure, and also we can plan the budget to manage our whole infrastructure. Adaptable, prefab structure members can be very small connections, members, and systems. So we can change our structural detail for the different purpose and different combination of a bridge system. So this is a new concept. So from this year, I will explain in many times what is the major concept of our research efforts for the structure. So last year, I had a chance to make this kind of a new concept for the resilience. As you see, in Korea, we had a fire on the bridge. It's a very the congested area that we have to replace in a short time, right? So we adopted the precast members, and also the supply chain from the steel material to the precast concrete, and also the company who can do the job in a site. That is very important part. We need to align the whole supply chain to recover this highway. And recently in Korea, I think in Japan also you have same problems, deterioration. We had a collapse of the bridge and people died. So when you have collapse, which is unexpected, so the authority to manage this structure, they have to replace this part. And we have natural hazard, more and more severe, even in Japan. So when you had a natural disaster, people want to recover the traffic service and also the others. So the prefab structure can solve this kind of challenges. The problem is we should prepare before this kind of event. So how to prepare? The first thing is automation or the ready design to recover this kind of structures. And second one is a supply chain for the material and members and equipment, right? And the third one is a specialized assembler in a construction site. Assembler need to have some way to pre-assembly because the different members can be delivered to the site. So we should have the way of the digital pre-assembly process for this kind of recovery process. So we did different kind of cases in Korea, but the problem is we didn't combine each other, right? Individual cases need to combine, and we should develop the system for this kind of resilient design and fabrication and construction. So we are discussing about the labor shortage and safety issues, and also the sustainability and resilience. So we have slightly different solution for this kind of issues. Productivity and pre-construction and minimal waste or CO2 emission and rapid recovery can be done by this prefab concept, right? So we will start from the BIM-based design, model-driven design, or the data-driven design. So data-driven design means the designer need to have data from the manufacturing side and the assembler side. Without those data, designer cannot prepare, right? So this is a big challenge. It's not easy. Companies do not want to provide their data to the designer. So this is the way we trying to solve in a research program. Another aspect in this kind of supply chain integration is we have to have the different suppliers in a single construction project. But the problem is that they don't know each other. They don't know each other. When you combine and assemble each members at the site, we need to know the details of connections. And sometimes we have to adjust the appropriate details. So this is way of design, manufacturing, and the assembly process. All the information and data need to be delivered to the designer, right? So this is a very challenging task for this kind of process. And also the supply chain need to recognize the prefab construction is different from the cast-in-place concrete construction, right? Even the workers at the site or fabrication factory, they need to recognize the difference. Accuracy of the tolerance, I mean the tolerance should be different. We have to change the specification. And then when you are ready to have the standard data on data delivery for this kind of construction, we can develop the automated fabrication and digitalize the inspection process and also the robotic assembly. Without the previous development, this is not so effective, right? So this is the one example we did last year for the highway bridge construction. So as you see, the design start from the model. You know, the designer just calculate and the generate reports, and based on those data, we draw the drawings, right? But we want to start from the model. Prefab supply chain, they have their own structures and members and connections. So we just discuss with them, I mean the designers, and then we have standard data format. And then when they do the calculation, the model automatically generated. So they don't need to deal with the BIM software. BIM software, it takes time for designer to be familiar with. Once we have the design models, and then from the model, we can derive the design, the quantity for the fabrication and some data for the automated fabrication factory. So those models and data delivered to the factory, and factory just use the some automated equipments, and they produce the members. After fabrication, we have to measure the geometry. You know, without cast-in-place concrete, you have to have the very strict tolerance requirements in 3D, not 2D. So we use the scanning technologies to measure the geometry, and those measured geometry need to generate the reports for the assembler. And these reports actually document in current situation. We have just issued the documents, whether it's okay or not. So even though we have some error of fabrication, but if it's okay, the data is just disappeared, right? Assembler do not have exact geometry of the members. But if you have more than 100 members at the site, and every member has a slight fabrication error, then we will have problems for the connection. So the digital geometry inspection data will update the original design models. Now, we have models based on the data, and inspection data will update the original design data. And using those, the updated model, we can do the pre-assembly, right? Before transport to the site. This is very important. Once we transport the member to the site, it takes a long time to solve the problems. So we try to use the BIM-based pre-assembly or also the AR-based pre-assembly process at the site. And from this, the process, we just reduce lots of problems of clash at the construction process, clash between the members and connections. So if you see the right below the portal, this is the full depth precast slab on a precast concrete gutter. So you see the several hundred connection parts, right? And the concrete member is, they have a time-dependent change of geometry, right? And we cannot control exact the geometry. Right? So we have to have a way to adjust and the solution to minimize the clash during the assembly process. So this is the information delivery process we did test last year. The problem is the companies who involved in this project, they are not familiar with this kind of a collaboration. And current contract do not have a consideration for this kind of process. They don't hesitate, they just hesitate to provide their data, right? So we have to solve this. This is just technology, but the process need to support the technology. So that is a current situation. Good. You know, originally the workers just fabricate the reinforcement, right? They bend bars and then they assemble. But we like to have the pre-assembled reinforcement blocks and then they place in the formwork and the cast concrete. That will they improve the current fabrication productivity. The problem is we changed the design. This is welded wire mat up to 25 millimeter diameter, and we can bend it to make the unit of reinforcement. So we changed the design using the 3D models, and also we just generated data for the fabrication. And fabricated member has a tag, QR code tags. And then the assembler know where to put the reinforcement blocks to the formworks. So this is one way to deliver the information from design model to the factory machine. And once we have the reinforcement and we deliver to the factory, this is the pilot factory we developed last 4 years, and the machines just place the formwork. But the machine need to have the instruction, which blocks placed where, right? So the standardized the members we should have. If you have very different shapes and the details, it's not easy to have the efficient fabrication. And then the concrete delivered to the distributor. And this distributor just know the how to put the concrete into the formwork, right? How much, how fast. We all have the instructions and define the efficient way of the casting concrete. And even the concrete need to be different, right? Concrete need to be different, right? So this is the process. Oh, sorry. After that, when he finished the fabrication, the members, the precast member can be cured at the curing chamber, and then we will measure the geometry, right? We will measure the geometry by the scanning. So for the pre-assembly, it is essential to have 3D geometry by scanning. Of course, we can use the photo scanning or the LiDAR scanning and laser scanning. It depends on the requirements of accuracy, I mean the resolution. So this is one example of the steel structure, steel bridge. Steel bridge fabrication need a hardware assembler from before delivery to the site, but it takes time and a wide space in a factory. So from the design, as I explained to you, we generate the 3D models, and from 3D models, we just produce the cutting plan. To produce cutting plan, you have information from the factory, right? By welding process, the geometry will be changed. So we need to know that. And then by scanning of each members, then we develop the part compare system to measure the error and they check the tolerance. And of course, through this pre-assembly process, the program will generate the inspection reports automatically. This is very important for the engineers in this company. Their major job is to produce this kind of inspection reports every fabricated members. This is another aspect, precast concrete members. As I told you, we did a pilot project for this highway bridge with the whole members of superstructures prefabricated in the factory. And then after fabrication, we have different approach to measure the geometry. One is the AR, augmented reality devices. We use HoloLens. So with the HoloLens and one AR tag at the members, we just fit the members automatically and take a photo. That is inspection, right? And then at the site also, we just do the pre-assembly virtually before the delivery of the members. So this is our approach. So from the office, factory, and site, we have to collaborate in real time, right? And another effort is the real digital fabrication using 3D concrete printing. This is very initial phase of this technologies. We start from the 3D models, aesthetic structures, and from the design models, we have to plan the code for the operation of the 3D printer. Printer need to have XYZ pass plans, and the speed and the shape of nozzles, everything should be defined for the fabrication. And after that, the pre-assembled reinforcing cage need to be inserted into the permanent formwork, printed formwork, and then cast concrete and complete the one segment. This is process. And then we will assemble at the site. So this is the process, digital design, printings, and pre-assembled, reverse, and casting concrete. And also we have to finish the surface for the durability. So we are using the robot arm milling to manage the surface. So from last year, we started to do the test of structural performance because we didn't have any design codes and specification for the 3D concrete printing in any countries, not yet, right? So by different material and different process of printing, we will have different structural performance. Especially the durability is a big issue, right? So when we design the concrete structure, we assume the homogeneous isotropic properties. But when you use 3D concrete printer, it's not valid, right? We have to have a way to design and assess the real process. The good thing is when you do the test, the first real permanent formwork members, the performance is really similar to the original, the reinforced concrete members with a similar design, the dimensions, right? So we will improve this kind of process. This is really automated members without the steel formwork. So the design need to be improved a lot. After fabrication, geometry inspection is essential, as I told you. But the problem is 3D geometry what kind of values we have to inspect? That is another issue. So we have to have a key geometry for the assembly. So in this precast concrete decks, the shear pockets for the connection, the location and arrangement is very important information. So from the scanning, we developed the data processing software to only extract data for the pre-assembly process, right? The other geometry is not so important. For example, flatness is not a good way to have the data from the 3D the inspection. So we just introduced this kind of technology for the inspection and also generate the inspection reports instead of current paper-based manual inspection. When we develop this kind of things, we are ready to do the robotic assembly at the site. Currently, we just focus on the very dangerous process among whole the process of the assembly. This is one example of the robot attachment for the erection of the heavy concrete girders for the bridge construction. As you see, the two attachments, just the erect the long and heavy girders. And recently in Korea, we have accident, collapse of bridge, as you see here, during the erections. So when we the lift up, the lateral the buckling occurred because it's 53 meters long and very slender bridges. But the problem is, as you see the red circle, there are two workers. It's so dangerous. Without workers, we cannot install this kind of bridge girders. But when you use this kind of the robotic attachment, we can minimize this kind of risk, right? Just they just have the positioning without the people around the dangerous area. So this is one effort to minimize the risk during the assembly. Okay? So this is all the research efforts for the prefabricated structures. And as I told you, we just do the efforts to have new value, like sustainability or the resilience, this kind of new approach for the engineers. The problem is how to collect the data and how to digitalize the information delivery between different participants. This is very challenging task for the construction industry recently. Okay, thank you.
Thank you very much, Dr. Shim. And the next presenter is me, I think. Hello, my name is Panjo Chun from the University of Tokyo. And let me do my self-introduction first. Though my presentation is from Japan side, my nationality is South Korea, and maybe in Korean, Cheil Kyopo. And I did, and in addition, I did postdoc in Yonsei University in Structural Engineering Lab, maybe in 2010, under Professor Yoon Mook Im. Anyway, this is my connection between Korea and my career. And anyway, sorry, the topic of my presentation is advanced infrastructure measurement using AI. First, let me start conclusion. First, of course, I will not end my presentation here, just first, I will show you the conclusion. I will present about the AI for point clouds or image analysis for infrastructure maintenance and buried pipe detection for safe construction. And in Japan, I don't know very well in other countries, but in Japan, ICT technology is initially being used in the construction sector and is now starting to be utilized in maintenance as well. And efforts are underway to create integrated and streamlined systems. For example, this is in Japanese, but let me explain in English. This is a PowerPoint slide from the MRIT in Japan. And from this slide, what they want to say is that this part, sorry, this part means measurement and design. Not only from the, not only on the measurement and design, but also for the construction or inspection after the completion of the construction and maintenance. They are going to use information they made in BIM or Shim. We call it Shim. So anyway, again, not only for the design and the construction part, but also we are going to use the information delivery or information system for the maintenance. Maybe in the previous presentation by Professor Shim, he talked about the deterioration. It is also a serious problem in Japan, which is the bridge collapse in 2022, if my memory is correct. The name of this bridge is Musota Bridge, and this is a water bridge. And this delivers the water from the left side and to the right side. And because of this accident, 200,000 people cannot get water for 1 week in Wakayama City. And of course, in some cases, which could have the kind of life-threatening consequence. In this case, severe corrosion and breaks were found in 4 of the hangars connecting the water pipe and the arch. This is a picture from the Google Street View. Of course, this is taken by Google car and taken in 6 months before the accident. And as you see in this capture, you can see broken here. Can you see? You understand, we can see sky. And it is visible on Google Street View year prior. And however, it was not discovered by anyone for a year. So, all of us, including my mother or my child, can see this one if they can use Google, but no one can find it. Of course, it is understandable. There is no reason to check this kind of photo from Google Street View. Because there is no purpose to check. From there, I can say that, of course, in the concept of the BIM, we are going to make lots of information, lots of 3D modelings, but the information is too much to handle only by human beings. So we need AI to kind of control or use this information effectively. And in Japan, we are now creating 3D digital twins of cities. These 3D models, this is digital twins of Tokyo, and you can access from the website. These 3D models are expected to have a lot of information, as I told you. So again, we need kind of AI to kind of use these informations. See, this digital twin is beautiful, but now we are kind of looking for how to use it. And this is one of the AI systems which I have invented. For the maintenance purpose, we need to kind of find the cracks on the concrete automatically. And this is the result of 10 years ago. We can see our AI can detect cracks very correctly like this. And from this result, we can kind of judge the health condition of the bridges in proper way. This is also as a result. We can see the result is very nice. So we can get not only large crack, but also small cracks. Of course, there are lots of commercial software to kind of detect these cracks, but sometimes the software outputs like this because they are dark place, and the software kind of judge these dark places as the cracks. So they made mistake. If it happens, we cannot kind of judge the health condition in good manner. So we need to kind of invent good AI to use it to handle the information. And also by flying drones, UAV, we can create 3D models combined with the AI mentioned earlier. And by kind of flying drone, we can automatically create 3D models and plot damages on them without manual intervention. By flying the drone, of course, they took the pictures, and by our AI, we can detect damages automatically, and we can develop the 3D model automatically, and we can plot damages like this. Actually, I can show how drone flies, but I don't know whether I need to do, because all of you knows UAV very much. But this is Skydio made by US, and we can kind of use this UAV and took lots of pictures, and using SFM or beam model, and we can kind of get information of the 3D structures of the bridges, and we can take pictures, and we can find damages, and we can plot it. And this is again, anyway, this is a conceptual figure of the 3D bridge model now we are making. The left figure is the 3D model, and at the same time, we can detect damages like this, so we can easily understand the bridge condition, though without going to the real place. And though this is the result of 6 or 7 years ago, but now our system's performance is better. And this is other story. Besides bridge inspections, we are working on detecting buried pipes. During the construction work, it is common to accidentally break buried pipes because their locations are unknown. I don't know the situation in Korea, but in Japan at least, we are not very sure where the pipe is. This causes problems for society, so we have developed technology to find buried pipes and plot them on the map. And this is our system. This one is a place for the experiment, and this is a car taking the getting the information of the underground. This is GPR system, ground penetration radar system. And this kind of emits the radar to the ground and get the reflective wave. And this is the image of the reflective wave. And from here, you can see this kind of shape. This is a kind of evidence of the buried pipes. And we detect, we make the system to detect these pipes using AI. And this is a experiment conducted in the city. This red one is real pipe information. And this gray one is taken by us. Because the reason why I kind of show only this one is that only here, only this way, the car can go. This is kind of for the pedestrian. From here, we can say that though it is not easy to kind of detect the depth correctly, because detect can be calculated from the speed of the radar go inside the ground, but the speed can be changed based on the water content of the soil. So we cannot kind of calculate the depth in precisely, but we can get good information at least. With this system, we did this experiment. With this car, we can get the information of the pipe. With this car and AI, we can get the information of the pipe. And we kind of move it to the database, including the maps. And from this database, we can kind of convey this information to this construction machine. This is a self-driving construction machine through the database using web API and wireless connection and so on. So if this machine, this unmanned construction machine, excavator can get the information of the buried pipe, and ideally, this machine can avoid breaking these pipes. It's controlling this arm. And this is a schematic figure of the machine and how we kind of avoid destroying the buried pipes. I don't know explain in detail because this part is conducted by not me, but other researcher in the University of Tokyo. But the concept is that if the machine can get the information of the location of the buried pipe, like here, they can kind of, the machine can make the path to kind of, we can say avoidance path, dig like this way, so that we can kind of avoid breaking the pipe. This is the experiment at PWRI where Dr. Moteki is. And first of all, we get the information of the pipe with this machine, GPR, and we kind of analyze it by AI and send the information to this unmanned vehicle, and we kind of dig. And this is the results of the experiment. And this is the first trial, of course, and this is pipe. And of course, in the first trial, there is no worry to destroy this pipe. We can, not we, the machine can dig like this. This is the second. This is third time. From here, the machine kind of understands that the pipe is kind of close. And this is the fourth trial. It is obvious that the machine tried to escape from the pipe. And this is the fifth trial. And like this, we can kind of make the entire system to avoid the accident from the construction process. And this is other stories. We also collect 3D point clouds in the bridge inspection, which are useful for the bridge inspection. And I will show you, and this is the 3D point clouds of the bridges. And what is the next slide? Oh. Sorry. And this is the 3D point clouds of bridges, and from this point clouds, and at the same time, we are taking the images, and now we are developing the algorithm to kind of make the fusion of the image analysis and point clouds analysis. Both of two has a good points. The image is, the resolution is very high, so we can see, say, cracks and so on. And the advantage of point clouds is that they have the 3D information. So if we kind of combine these two, we can kind of make good information of the existing structures. And I also took, in Japan, at the beginning of this year, we have very severe earthquake, January 1st in Noto, in Japan, northern part of the Japan. And, lots of bridges or infrastructures are damaged. And this is the example. And I got the point clouds of this part and I got image of this one. And from here, for example, we can kind of measure the width and the length of the cracks. And this information can be used for kind of modifying these bridges. And at the same time, thanks to the point clouds, we can kind of calculate the tilt of the pier. And though this bridge is used, now we kind of decide to use this bridge, though bridge pier is kind of tilted like this. Now I think it is not very dangerous, but it's better to keep monitoring it. And for the keep monitoring the bridges, these point clouds is very good information. And now I come to the conclusion. And again, now we are developing the algorithm to kind of make the fusion of the point clouds analysis and image analysis to get a good point from both of them. And in Japan, ICT technology or I-construction or smart construction is not only for the construction, but also for the maintenance and so on, entire process of the infrastructure. And today I kind of introduce these things in this presentation. And thank you very much for your kind attention. Thank you very much. And from now, I'm moderator of this symposium. We are going to the question and answer session or discussion session from now, but we need to prepare the desks. So please wait some time. And, if there is no question, the question and answer session will be very kind of not good one. So please kind of come up with good questions and please ask us. Oh, okay. Later. Okay, then please wait 5 minutes. We need 5 minutes to prepare. Okay, then question and answer session will start from now. Though some of them are going out to smoke or I don't know, but anyway. But anyway, my name is Panjo Chun from the University of Tokyo. And, now in JSC, lots of participants or audience are Japanese or Korean. So kind of we are going to try trilingual things, we have Korean interpreter and maybe lots of people understand Japanese and English. So I'll ask interpreter to interpret to Korean or sometimes to Japanese. And first of all, we are going to start from the question. First question is that, please wait. Is there any priority list of works based on safety concern, which are more risky for human labor, but we can use unmanned construction for those works? For example, work at height, underwater or underground, from the Saitama University. And I think this is for question for Dr. Moteki, I think. So can you answer? There is one.
日本語で日本語で喋らせてもらいます。いずれも安全を確保する必要があります。で、優先順位は特にないっていうか、あれですよね、水中とかですよね。いずれも優先順位っていうものはありません。で、人が立ち入ることができない危険な箇所で活用をする必要があるという形で、日本では水中だとかですね、あと地下での作業というのは、必要に応じて無人化施工というのはもうすでに適用されてます。はい。
All of them need to be secured, and there is no order of priority, and they must be utilized in hazardous areas that are inaccessible to humans. And in Japan, unmanned construction is utilized for underwater and underground work as needed. And this is, and maybe in Korean, please.
もう一回一文章ずつ話してくれると。
マイク。
あ。
もう一回一文章ずつ話してくれると、それを
わかりました。
参考で
はいはい
翻訳しますので、
はい。いずれも安全を確保する必要がある。
어떤 것도 안전을 확보할 필요가 있다고 생각합니다.
で、あと、優先順位は特にないです。
우선순위는 딱히 없고요.
で、人が立ち入ることができない、危険な箇所で、活用する必要がある。
사람이 출입이 어려운 이제 위험한 장소에서 이걸 활용해 나가고 싶다고 생각하고 있습니다.
契約してないんだけど、リスクを検討しています。
그 리스크도 검토하고 있습니다.
で、日本では水中、地下の作業で、すでに無人化施工は、状況によって使われている。
일본에서는 수중이나 지하 작업에서 이 무인화 작업은 무인화 시공은 이미 사용되고 있습니다.
I don't understand Korean, so is it okay? Okay, the next question is that how efficiently we can get live data of on-site construction for analysis to solve any on-site problem at office, so that we can reduce the construction project duration or can go with the schedule. I'm not very sure this question is to whom.
I talked about the automation of the whole site, and his question is about the construction progress schedule monitoring or construction problem monitoring of the site, not only the equipment or individual labor. And many approaches are taken by using vision technology. You know, for checking, evaluating the soccer players' activities, they use vision and AI image analysis to how long they worked, how fast they worked, how many times they touched the balls. It's the same concept. So by using vision quickly, they check the status of the equipment fleet, check the status of the equipment fleet, and also the platform. I showed our Earthwork platform. For that kind of work, we use periodic drone data. Actually, our research program is utilizing drone map updating twice or three times a day for a construction site, which can be doable. And that way, we use vision-based live monitoring plus model-based progress or problem monitoring. I think that's the way to go. It was in English, so I think everybody understood that. 그 전체적으로 봤을 때 이 질문은 다시 한번 좀 잘 읽어보면은 on-site construction analysis for it's saying project duration and schedule이면은 construction 우리가 소위 얘기하는 construction management 관련된 이슈거든요. 근데 얼마나 지금 진척이 됐나 그리고 어떻게 빠르게 일을 하고 있나 하는 것은 이미지 어널리시스 같은 라이브 비디오를 해석을 함으로써 또 파악이 가능하고 저희 프레젠테이션에서 보여드렸던 드론 데이터 프로세싱을 조금 피리어드를 줄이면서 빨리 해서 그 프로그레스나 어떤 프로블럼을 체킹하고 파악할 수 있다고 생각이 됩니다.
죄송한데 혹시 한 문장씩 나눠서 말씀해 주시겠어요?
Okay, let's just stop it. I answered it in English, so yeah. Okay.
一文章ずつちょっと話してほしいんですが。えーっと、
Sorry for because I didn't kind of plan thoroughly, so sorry for that. And okay, next question.
Can I have a comments for the structural aspect? 우리말로 할까요? 예.
한 문장씩 해주시면 바로 동시 통역가
네.
있습니다.
구조물 분야에서는 크리티컬 패스를 놓고 실시간인지 아니면 타임 갭이 좀 있어도 되는지를 우선 고려를 해야 됩니다.
構造物分野ではクリティカルペースを置いて、
리얼 타임.
リアルタイムか、時間の制約があるか、ちょっと考慮しなければならないと思います。
현장에서 이제 아까 보신 그 건설 장비 중에 로보틱스가 있으면 리얼 타임이고
現場で見るその建設装備の中でロボティクスがあったらリアルタイムで、
geometry 인스펙션을 하는 걸 가지고 코디네이션을 해야 되면 타임 갭이 있어야 됩니다.
ドラマティックインスペクネーションをやる中でコーディネーションをやらなければ、時間の順序に
타임 갭이 있다고.
時間の介入があります。
보통은 이제 사업자가 다르기 때문에
それは事業担当者が違うため、
각각의 그 공정마다 시간의 이 갭이 있어요.
工場になるよ。
공정, 프로세스.
それぞれのプロセスの中で時間のその関係があると思います。
그래서 이제 정보를 전달하는 사전 약속이 있으면 이 갭을 최소화할 수 있고 크리티컬 패스를 줄일 수 있습니다.
情報を伝達する事前のルールがあったら、その사전 약속이 있으면 뭐죠?
이 중간에 있는 그 시간, 이 비는 시간을 줄일 수 있다.
その間にあるその空いてる時間を減らすことができます。
다른 하나는 이제 우리가 그 교량 건설 같은 거 하면 가장 많은 그 지연을 일으키는 것 중에 하나가 기상 기후 관련 내용입니다.
もう一個は、橋梁の建設とかで行う一番大きな遅延の要因は、気候とその天気に関連する問題です。
그래서 구조물 쪽에서는 프리팹을 하는 이유가 짧은 시간에 공정을 완료해가지고 이런 이제 기후에 대한 리스크를 최소화하는 게 하나의 이제 목적입니다.
構造物分野でプリパップをやる理由は、その期間をなるべく短くして、その気候などのリスクを減らすことが主な理由です。
제가 데이터를 물어보셨으니까 아마 질문이 현장의 데이터를 어떻게 얻어서 공사 기간을 줄이거나 공정 관리하는 데 어떻게 활용할 거냐를 물어본 것 같아요.
現場のデータをどうやって求めて、その工場の管理に使うか、その時間を短縮するかに活用するかに関する質問だと思います。
그래서 건설 현장에는 굉장히 많은 데이터가 있죠.
建設現場には数多くのデータがあると思います。
그 데이터를 잘 얻어서 활용하는 게 중요하지 않겠습니까?
このデータを効率的に求めて活用するのが大事だと思います。
그러려면 그 데이터를 어떤 규격으로 만들고 즉 표준화하는 거죠. 그다음에 어떤 방식으로 데이터를 주고받을 것인가의 약속을 정해야 됩니다.
そうしたらそのデータをどうやって標準化してどういうルールでやり取りを行うか規定しなければならないです。
그래서 데이터를 규격화하지 않고 주고받는 방식을 정하지 않으면 현장에서 데이터를 활용을 해서 활용하는 게 불가능하게 됩니다.
なのでそのデータを規格化せずにそのまま利用しちゃうと現場からはそのデータを活用することができないと思います。
여기에는 또 하나 중요한 게 통신입니다. 통신.
ここでもう一個大事なのが通信です。
어떤 통신 방식으로 데이터를 주고받고 저장할 건가 하는 것도 규칙을 정해야 됩니다.
どのような数詞方法でデータをやり取りするかに関するルールを決めなければならないです。
한국 속담에 구슬이 서말이라도 껴야 보배가 된다. 아세요?
えっと、
그래서 그런 규칙이나 규격화, 통신 방식에 대한 정의를 반드시 해야 데이터를 이용을 해서 공사 기간을 줄이거나 그다음 페이퍼리스, 어제 국토정상에서도 그런 이야기를 했는데 그게 가능하게 되는 겁니다. 그렇게 생각합니다.
その規格がその基準をちゃんと決めなければ、今のさっき発表でおっしゃったペーパーリスとか、そういうことがちゃんと行うことができませんだと思います。
Now I found that, if discussion is longer, to translate Korean to Japanese is okay, but, from here English is kind of impossible. Now I find, sorry for that, but, before doing that, I cannot find it. Sorry. And next question is regarding use of, this is for me, I think, regarding use of GPR to detect underground pipe system. It is possible to detect diameters of individual pipes in case where we have complex underground piping system occasioned by planning. For example, having multiple pipes for fiber cable, water sewer system, and so on. Thank you very much for the questions. And of course, I was trying to do, and theoretically it is possible, but according to the experimental results, it is at least the accuracy is not very good for the diameter and so on. And this is my answer, and maybe in Japanese, 計測はできるけれども、精度が非常に悪かったと。そのぐらい韓国語で伝えてください。
캐치는 가능했지만 정확도가 매우 떨어졌다라고 전달해 달라고 하십니다.
Next question is that how much precision or accuracy is considered during measurements using AI technology? Sometimes, maybe for me, sometimes small deviation from a certain point cloud, maybe cloud results, maybe a large deviation after construction in 100 or more points. In that case, how to minimize it after a certain point? Suppose if we have 200 points to construct, we can adjust or correct it manually after every 50 points. Sorry, it's not easy to get question precisely or accurately. But anyway, if I kind of focus on the precision or accuracy during the measurement using AI technology, of course, it is based on the use case. And so, first of all, we need to kind of decide how much we need, how much accuracy we need, and we need to kind of develop the AI technology to satisfy this condition. 最初に、欲しい性能をちゃんと定義した上で、決めた上で、それを満たすように AIテクノロジーを開発していくことが大切ですとお伝えください。
최초에 요구하는 그 정확도를 정확히 정한 뒤에 그 다음에 AI 기술을 활용하는 게 중요하다고 생각합니다.
And maybe the last question from the audience, or not Zoom, So 교수님, could you share about the current status of combination of BIM and robotics in 3D printing technology in Korea? Not so. I think Professor Shim.
예.
Maybe.
이것도 우리말로 해야 되나? 제가 보여드린 그 3D 콘크리트 프린팅 장비는 두 종류가 있어요.
と発表で紹介した 3D プリントコンクリート装備は2つの種類があります。
XYZ 축으로 움직이는 요 G 코드로 운영하는 로봇이 하나 있고,
또 XYZ 軸で動く G コードで運用するロボットが一つあり、
6축 로봇 아음을 이용하는 프린팅이 있습니다.
6軸ロボットアームを用いるロボットが一つあります。
3차원 모델링을 구조물을 하게 되면
構造物をモデリングするとしたら、
그 로봇 끝에 있는 노즐에서 토출되는 콘크리트 두께, 그다음 폭, 이 정보하고 노즐의 스피드, 경로 데이터를 뽑아내야 됩니다.
ロボットの先からその分出するコンクリートの厚さと、ロボット、뭐였죠?
노즐의 폭, 두께, 속도, 횟수.
ノズルの幅と厚さ、そしてその分出速度の情報が必要です。
이거를 이제 3차원 모델 정보에서 추출하는 프로세스가 있어야지
그래요.
구현이 가능합니다.
これを3次元モデル情報から抽出する技術がなければ、
굳지 않은 콘크리트는 내가 원하는 디멘전을 컨트롤하기가 어렵습니다.
固めていないコンクリートは、今、設計者が求めるそのディメンジョンを定義するのが難しいです。
그래서 콘크리트 재료 배합 개발이 굉장히 중요한 파트입니다.
なので、コンクリート材料の配合計画がとても大事だと思います。
그리고 한 재료에 대해서는 컨트롤하는 파라미터가 한 가지입니다.
一つの材料に対しては、コントロールするパラメータが一つです。
그래서 장비가 같더라도 재료가 바뀌면 이 컨트롤 파라미터를 다시 정해야 됩니다.
装備が同じとしても、材料が変わったら、そのパラメータを新しく定義しなければならないです。
그래서 설계, 재료, 장비가 한 패키지가 되는 기술이에요.
なので、設計、材料、装備が一つのパッケージになる技術だと思います。 この3次元モデルが BIM の技術を意味します。
Is correct. In your presentation, there is no specification for the 3D concrete printing. And the situation is similar in Japan also. And now, in JSCE or JCI, Japan Concrete Institute, we have committee to make the specifications or try to kind of make specifications for 3D concrete printing. And I also member, but kind of member only in the name. But anyway, now we also try to do.
There is a challenging issue is that all the material for concrete printing, they have their own patent. So we cannot build a design code or specification for the patent technologies. So that's a problem.
Yeah, I agree. And I think his boss is the head of the committee. But anyway, thank you very much for answering questions. And if there are any questions from the audience in JSCE, we can kind of accept it. And if no, if my memory is correct, Dr. So kind of raised the topics for the discussions. And I kind of took memo of your yes. Okay, if there is no question from the audiences, let me kind of share Dr. questions. Please wait. I think I kind of took sentences and put it to the PowerPoint. Share. And this is if I didn't make mistakes, this is a questions from Dr. So. Issues regarding the development and the use of autonomous robotic earth-moving equipment. It is slower compared to manned equipment operated by skilled operator. So productivity decreases when unmanned autonomous equipment is used. Of course, it is very serious problems. And I think from Japan side, Professor Nagatani is a specialist of this question.
So first of all, let's define the productivity. So then something output divide the number of the people and the time. Should be one easy definition of the productivity. So automated construction, once we realize fully automated construction, then we can divide by 0. Then productivity should be infinity. So actually we can reduce once we can reduce the workers, then productivity increases. Then to answer for this question, then let's reduce the worker. This is one easy solution. And another important part is the automated construction machines can work in the day and night. Then we can increase the time of the working. So typically, particularly in Japan, the worker should work outside less than 8 hours, but it can work 16 hours or 24 hours. This is another easy answer. However, actually we know that at least once we do something with autonomous construction machinery, then it's a double or triple slower than the human operator. Then of course we want to make a safety. Then we don't want to increase the speed of the machinery. However, we need to have a balance between the speed and the safety. It's very important. And another part, yeah, I have. So let's talk about not the autonomy, but teleoperative construction machine. Then the interesting part is a skilled operator is not equal to the skilled teleoperator. And I saw that this is an interesting experience for me, that one guy who was test working on the site with not a standard workers, but a gamer, gaming guy. It seems like very white face. And he's very good at controlling the teleoperatively, controlling the teleoperated construction machines. And I believe that he is not good work on the standard one because of, so we think that he's a very good talent to construct a 3D environment inside of his brain. However, we always ask the guy who is good at control the standard construction machine. In this case, he has to have a difference between the standard one and also teleoperative one. It might be a big gap for him. Then we should change the mind to test for such kind of guy. Particularly the gaming young people should be good at. Yeah, please.
You know what? These questions are actually I have answers and they're pretty much same. And I asked this question to the Hyundai construction equipment company's workshop, and I asked that question expecting some good answers because they are working on the unmanned equipment, but I had to answer. First question, exactly same. It's the productivity about the equipment or labor productivity. Even though the unmanned machines has lower productivity, if one operator can 2 or 3 machine, the labor productivity goes up. And as I said, this labor shortage problem in Korea, like a rental cost for 30-ton excavator is $5,000 per month. And operator wage, exactly same, $5,000 per month. So that means with the labor productivity increase, you can have a good economic effect. So it's worth trying, unmanned operation. And like Dr. Nagatani's operation, we saw the dandori operation. For dandori operation, we are not there yet, but we need to be very selective. Some dandori operation, like a spreading and compacting that I showed, you can do it with unmanned. And I don't know whether the Trimble folks are here, and Trimble, they have an unmanned system, but actually effective unmanned system is one operator using dozer, teleoperation dozer, and compactor is following. That's autonomous. So one operator operating 2 machines. Only for that you can have a better labor productivity, resulting in the system productivity increasement. So we need to work on the this unmanned construction for sure. And as time goes by, that the scope of the dandori work that we can take care of with the unmanned machine will be bigger. So we need to work on that. And the third one is that's an easy question actually. It's for autonomous vehicles. There are many uncontrolled cars around the autonomous cars, and so high risk of the safety accident because it's not controlled environment, but construction environment, you can control it. You can control the excess of the labor, and using kind of virtual fence, you can specify the work for unmanned machine. So with that, it's a much better environment for going for autonomous. And second one, I'll answer it later, or
So if you have one sentence answer, though this question is very difficult.
I think we have one important person from HD construction equipment company. And, they are working on the R&D process for unmanned dozer and unmanned excavator, even the loader. I noticed that, and you guys are working on that, and but it's still at the R&D stage. I know Volvo is very aggressively advertising their unmanned equipment, but still advertising. You cannot see it on the market yet. So before like a Volvo or Komatsu or HD equipment come up with a commercial unmanned system, the only way is to retrofitting the current equipment. And retrofitting itself is pretty expensive, and for feasible dandori work, we can use that master slave control unit, which is not very accurate, and but still that's the interim solution that I think to utilize these unmanned systems at the site. That's my answer. Yeah.
Yeah. Of course, I understand it, 1, 2, 3, especially 1 and 2, 3.
Question? Yeah. We have talked about earthworks related technology to enhance the productivity. Let me have a chance to introduce another man of our TC30 member from Germany through Singapore, Mr. Tatsuki. Because Tatsuki is working for Hanyang, the very competitive tunnel boring machine manufacturer in the world. Let us think about tunnel boring machine. There are so many components to consist TBM. I guess in older days, there are so many people needed to operate or control TBM machine. However, nowadays, the number of operator is decreasing now, right? So how about to answer to productivity enhancement in example of TBM?
Thank you very much. Thanks for giving me opportunity to talk here today. I was thinking what is similar between Earthwork, because it's pretty much developed already, then some other topics, and then what does it mean for tunnel boring machines? And you spoke about drill and blast, but just about the small part of that. So everybody is asking to make our machines more efficient, more faster, and more safe. At the same time, we have issues to get skilled workers. Nobody wants to work in this environment. And at the end of the day, a tunnel boring machine is a mixture of mechanical parts, geotechnical understanding of the ground environment, a lot of process technology behind, especially when the tunnel is very long, machines going in and out. It takes longer and longer as the tunnel is. And lastly, as well, civil engineering. And we as TBM supplier today are actually just focused to make the process inside of the machine more safe. So the dangerous part in the tunnel boring machines today is heavy loading, right? So we have, for example, road segments, or we have concrete segments. Some of them are 10 tons, 15 tons heavy. And we don't principally want that anybody is close to this kind of movements of heavy load. So this is relatively easy with sensory technique and with some extra equipment. And we have already experience done on different job sites like in UK or in Australia nowadays. Then the other part where we are very focused is how to predict that the machine is finding the way without too much influencing from our side. So today, if the operator has a good day, maybe he is very alert to difficulties in the ground, then he's steering the machine. If he has a bad day, so normally the night shift, then they are sometimes going out of the alignment. Of course, there are alarming systems and so on, but this is actually not sufficient enough for our requirements. So we want to find a way that the machine principally can autonomous drive through the geology or through the ground. So then you need a sensor system like what you did with your pipes, right? Your radar pipe system, but I can see the accuracy to read it as well, the data, very difficult, right? We have the same issues. We have different systems installed on the machine, but nobody can read it really. So, or you have an expert with a lot of experience. So there are certain limits as well, right? So this is maybe a difficult task to fulfill for the next, let's say, 10 years. But nevertheless, that's everybody's asking for it. And then last but not least, the maintenance of the machine. So for example, we are thinking today, you have a lot of spare parts on the machine which need to be changed. So what would happen if some of the spare parts, a key one, would give a signal somewhere, and then you know automatically you need to replace it. Otherwise, the machine breaks down. And then even further thinking, the replacement goes automatically to a storage yard, and the storage yard, there is somebody and said, aha, we need to send it next week for changing because there's a shift, whatever. And then we have opportunity to change it to reduce the downtime. So there are a lot of ideas, a lot of things, but at the end of the day, of course, you need as well a contractor who is willing to pay for it, an owner who is willing to invest into it, and so on. But there's a wide field of things what we can do and improve. And for tunnel boring machines, lastly to say, the disadvantage if you, for example, talk about an excavator or heavy equipment for earthwork, like from Volvo or whatever. These machines are quite unique. So from project to project, they're different. So if I go in mass production, it's maybe easier to implement new technology, but for us, it's a bit difficult because it's really project-wise. And if the project is not good financed principally, then of course it's more difficult to introduce it as well with new technologies. But it's a very interesting field, and we are investing from our side as well in Germany, in our headquarters, with our own R&D team into this field. Thank you. Maybe difficult to translate.
And, we can do the discussion forever, but, we may have the time to clean up this room. So I think it is time to kind of close this discussion session. Thank you very much for very good discussions and comments. And from after that, we are going to ask Dr. Cho to do the closing remarks. Maybe here, can you do?
Thank you, Professor Chun, as a moderator and the co-chair of TC30 of ACECC. Thank you very much for your participant to this meaningful and useful seminar in Tokyo, in Japan, especially at the Japan Society of Civil Engineers. Yeah, as I said already, digital transformation is already new normal in our industry. So let's go forward through digitalization for our industry. Thank you very much for your joining today. Thank you.
Then we kind of end this symposium. Thank you very much for all participants.